And good morning, Doctor.
Good morning.
How are you?
Good. And yourself?
Good. I'm good too. Everything is okay.
How is Popocatépetl?
I don't hear too much, but I think this is coming a custom.
Yeah, it's yeah. Yeah, my wife's complaining about it.
Oh, I remember your wife is in Cholula.
Well, Dr. Page is with us too, I see.
Sorry, I was preparing a coffee while we are waiting for Dr. Page. He is not yet, or is yet?
I see his. He looks like he's there, but
he's
but
connected yet. Yes. I think
I have a small problem with my audio.
Okay. Yeah, I can hear you.
Okay. Do you hear me okay?
Yes.
yes.
Okay, that's better. Okay. So, good morning. Here we are again after 3 weeks.
Good morning. How are you?
I'm fine, thank you. So this morning we're going to be talking about category theory, I think. Jesus, you were...
I see. Then I don't know what is if there is some problem today. I say the Professor Garrett that I think that it is the custom now from time to get higher I don't know how I can say it, because it is not an eruption, but only kind of in species fumarole. I don't know how late.
A lot of smoke.
It's from the volcanoes.
A lot of smoke.
Yes.
A lot of ceniza, a lot of volcanic ash.
Volcanic ash, volcanic exhalation, but not volcanic.
No lava, just a bunch of
no lava. You don't want the lava part,
which you don't want to breathe. It's got all kinds of heavy particles in it, crystals, and it looks pretty. They're canceling all flights basically out of Puebla. It's a difficult time, really. Half the flights are canceled.
How is the air quality in Mexico City?
Just the air quality is
Very bad. I hope not quite so bad
and then
to the north.
to the north,
Where you are in Cautitlán.
but
Cleveland is
in,
California.
to the north of Mexico.
Campo Uno, Campo
But
Cuatro.
the Campo 4.
Uh-huh.
They are spread in, Professor Pesh, places in two different, near Juan from.
Yeah, your audio is
the
breaking up or something. It's not perfect.
Yes, I'm having a bit of trouble, and seems as if Jesus has been disconnected suddenly.
Okay, Brian is here too, I see.
Uh-huh.
Yes, I can see. I have problems with the connection in my iPad. I can see that the connection is good. My home,
Right now, I don't see any audio or any video from you, Jesus. I still have some audio, but I'm not sure.
I don't have video either.
I have your
It's your audio is broken up.
hear me.
Okay.
Now I can see you.
Yes, I don't know why, because my signal here is looks like good, but Duncan, hear me?
Yes.
Yes,
Yes.
it's okay now.
Okay. Okay. I hope this work. Okay. Mhm. Okay.
All right. So Brian has joined us, I think. And good morning, Brian.
Yeah, good morning to everyone. Good morning.
Okay. And Jesus, this morning you were going to talk about category theory, I believe. You were, I think you said you had a few
Yes.
slides.
Yes, I am going to put my slides. Only wait for a moment, please. And okay. I am looking for the slides. A moment, please.
might say that the talk I gave and that I talked about the last 3 weeks ago, there's a very strange problem. It's not quite correct. It might change the way this duality and what I call local duality in relationship to category theory changes as well. What's wrong with that formula, Heron's formula that I gave, was you had to replace, to get really Heron's formula, the area squared, you have to replace the distance between the vertices with the distance squared divided by 2. A very strange situation, but I'm working on trying to understand exactly better. But also I'm working with Dr. Havel at MIT, and he's done extensive work on this generalization of Heron's formula for the triangle, and very interesting ideas that he's able to contribute to the same. Well, he's generalized it to infinite dimensions, but that would be a topic of another talk, because maybe I'm going to invite him to join us if he would like to join us. I think he would be an excellent contributor to some of the ideas we've been talking about as well. At any rate, I'll give it back to Dr. Cruz.
Thanks. Okay, I'm going to put my slide, and I'm going to share my screen. Can you see now my
Yes.
screen?
Yes.
Okay, thanks. Okay, the title is tentative. The idea is to speak about the duality concept in category theory, and finally try to apply to Clifford algebra. I started here with the normal definitions of in category theory. I think I do not stop here, but only I wanted to put this again, that principal definitions for category theory. And then I wanted to I want to go to the definition of duality. Then wait a moment, natural transformation, and finally I think duality here. Okay, we have the speak about the concept of duality in category theory, and I think that we can say that it is fundamentally sorry, okay, and I think that one of the principal parts of this definition is here when we invert the direction of arrows. Then, in fact, it's used to say that duality is the process of reverse all arrows. And it looks like simple operations, but this is important for building new categories. And then we can, for example, to build a opposite category. The idea is that if we have here a category, sorry, if we have here a category with different objects. For example, we have the category C and objects A, B, C, etc. And we have here morphemes like this. If one, if two, for example, then in the opposite category, we have the same then the objects in this category are the same, but the arrows are inverted. Then here we have G, G1, G2, and Gi is equal to Fi opposite. Then we only inverted the arrows in the category, and in this way we get the opposite category. Then the duality principle used to help to us to build new categories, but not only to build new categories, but we can add that all the statements that are wielded or that demonstrate in a category, MacLean used to not statement sigma letter, then all the statement that is only a construction of enunciates that are wielded in the category C, and if this is a true statement, then we can say that one statement in the opposite category can be formulated only replacing the arrows in C with the arrows in C up, and then the statement is true. Then this is important here, and in the table that we see here before, we can see an important thing that that I forget to mention, that the composition is inverted. Then this is important for the duality concept, and not only the arrows are inverted, but the composition ruler is inverted too. Then with this, we can build different kind of categories, and to show some properties in this new category without need of demonstrate them. Oh, sorry, I put two times this slide. With this idea of work with the opposite categories, we can define two kinds of functors. Then we can speak here in terms of a covariant functor that works in this way. When we go from one category to another category, how I have said before, the functors take the every object in the C category and go to the same set of objects in the new category. But we can work here I am referring to this like the image of the body C in the new category. And this is for all the categories. But it's the same for the, if we take the, I'm going to put the name here and here the opposite category. And if we take bodies in the opposite category, then there are opposite functor that takes objects in the opposite category and relate with objects in the original category. And then this relation can don't change in any way, but the relations between objects, like we can see here, for example, transforms in the sorry. I am presenting the I wrong in my in the before presentation. I need to repeat here. I need to erase all this because sorry, I was here speaking about the category C and the opposite category. but here that we have is two categories. The category C and the category B. And the functor take objects in category C to and relate with objects in category B. But we can, and I'm going to change here the color. For example, and if we can put here the opposite category, the objects are the same, but we can take objects in the opposite category to the category B. Then this is the opposite category. And then I take one object in the opposite category that is the same object in the initial original category, and then I use a new functor from the opposite category to the new to the B category. Then the objects are not changed because I take the functor T or the opposite functor T. But the relations are working in this way. If we take H, for example, here in the category C, then the functor T take these morphemes to the functor, to the morphemes TH. But if we take the opposite category, if we take the opposite category, for example, here we take the this arrow. I'm sorry, it is so difficult to change color. But I say, if we take now a morpheus in the that I am into this morphemes, this is H in the opposite category. And then we take now the relation T opposite acting on H it's better to write in this way. The H opposite, because I am taking this to to a new category here that is the B opposite category. Then a covariant functor take the arrows in the same way that the original functor. This is the principal idea. I think that I needed to, it was better two different pictures here for the relation between the categories C and B, and in a separated picture, I need to put the relation with the opposite categories. Then, because I think I don't know if it is too much confused here. But
The picture is
the principal
complicated.
idea, yes, it is complicated, and I have not too much space here, but I think that if I change for a while, I change here to the Blackboard. I think that it is better. Okay, then we have here two categories, C and B. And maybe we have a C1, C2, these objects here, and B1, B2, B3. Then I can use to define a functor that relates, for example, and take the objects in category C, for example, and the image of C1 is B1, and so simplifying here the relation is 1-to-1. Then this is the way that I can sorry, 2 and 3. This is the effect of functor T on category C, mapping to category B. But I can build the sorry, but we have not only objects, but we have morphisms in each category. And I am going to use this to use this color here. Then I am going to speak here of if F1 and F2, for example. And then I like to take this morphism here into the category B. Then I take, here is T on if F1. And then I get here the mesh G1 that is equal to TF1. And so for the others arrows. Then I am using the T functor here. But I can now work a category. And then the opposite category have the same
Are you still there, Jesus? Are you still there, Jesus? Oh, you seem to have disconnected. Dr. Supchik, are you still there?
Yes, I don't see Dr. Cruz
No,
or yeah, Dr. Cruz is not there anymore.
No, he seems to have disappeared. Has some network problems, perhaps.
Well, maybe he'll come back.
Yes, I hope so.
Yeah, I'm wondering, in the chat, can you send a picture in the chat box?
Yes, I believe so. You can drag it into the chat box.
Okay, I'm thinking about doing that. His sets of C and B, I can almost demonstrate my so-called local duality in terms of two such sets. That's very interesting, I think. I'd like to share a picture with him as well, but of course he's not there yet. But it's interesting. Maybe that will help relate it to category theory more closely. In fact, I can even describe it. I'm going to put in the set C, I'm going to put B, and then B prime, and B double prime. But I'm not saying what that is yet. And then in the set B, I'll start with B as well, but then I'll write down for the second element B prime, B, B prime. And then for the third element, I'll take that, go B, B prime, B prime, and B. And what I hope to show by that is that if you look at, let's see, is that right? Let's see. Yeah, B.
Perhaps can you try a whiteboard and draw it on?
Well, I don't have a whiteboard. Let's see.
It's a function within
maybe I can. How do you get the
share
whiteboard?
screen.
Uh-huh.
If you go to share screen, you have the option.
Oh, okay, I see it.
to-
Okay, let's see if I can do that.
Yes, I see what you're doing.
Okay, okay, here, okay, let's try it then. So I want to draw two sets. I'll call this C. Why can't I do it? Oh, okay. So I'll write this as B here. See, how do I do that? Okay, I don't know why I can't. Oh, here it is. Okay.
Takes a bit of practice to get that.
Okay,
The
let's see.
drawing
I want
function.
to put a text inside this box here. I want to write on that though. Let's see. Why can't I write? Oh, maybe I have to do this. No, can't do that either. Okay, I'll have to practice that. It looks very useful.
Yeah, when you have the option to annotate, I guess. In the annotation, there's a little
Okay,
list of icons with the T is the one that will let you put text.
Okay, let's see how this is going to work. B prime. Let me write a prime here. Well, I'll have to practice more on it, but yeah, it looks very powerful actually. I never have tried that. Should have learned, of course, that.
Yes, I see that you've written something there.
Yeah, I wanted to write a prime here. I don't know how to put a prime on those B's. Or I wanted to write B prime and B double prime on this box. But, well, anyway. Let's maybe start over again or something. Let's see, B. Oh, okay, I'm back into it. Okay. So, okay, maybe I can do it here. B. Okay, I want to get rid of this. Okay, I'm going to clear everything again. They're all drawing. Okay, I'll start over again now. See if I can do any better this time. So this is going to be one box here. And now I want to write here B prime, and B double prime. And I want to put an arrow in here. And I want to write a second box here. I'll make it bigger. Okay, now I'll write here, I'll write B. And now instead of writing B prime, I'll write, well, I'm going to write B prime again, but I'm going to write it as B prime, B, and B prime like this. Now with my concept of the multiplication table, if I consider these all to be nilpotents, then B is a nilpotent, and B prime is a nilpotent times B prime, and the product of those things, if they're locally dual, is B prime. But now if I do it a second time, so now I want to take the prime of this thing. So I want to take this thing, B prime, B, and B prime here. And I'm going to take this thing prime here, and I want to multiply that times the previous one. Okay, now if I take this prime inside that, then what I get is B prime B. So I'm going to say this is equal to, okay, what I get is I get B prime. Well, again, so B double prime is B again. And then times this one, B prime, B, and B prime. But this thing, this will give me, let's see if this is going to work. This will give me B prime here. Oh, okay, let's see, it's not going to quite give me what I want. I wanted to just get, okay, well, this is going to, I'll tell you what this is equal to. This is B times B prime, B and B prime times B. Ah, that's what's wrong. So this will give me B prime and this will give me B. Oh, okay, so this, yeah, this shouldn't be here. So
You're
what
missing one more term.
I want to get back to B. I want to get back to B here. Let's see. Oh, so I did this wrong. This step is wrong here. You have to cross this out. When I apply this, take the prime of this thing, I multiply it by B on each side. So when I write down, I get B times B prime times B times B prime. Oh, okay, this is what I want now. Times B. And that's, okay, so this will give me a B. Let's see. Now that's equal to 0. That's not right either. But the idea is, I want to use this idea of a local duality to get back to, well, we know that B double prime is equal to B here. So I'd like to, yeah, so this takes B into B prime here. Now I want to get back to B. So if I write this as B here and B here, well, that will give me 0 because B prime, but my duality is that this thing here is equal to B prime. Okay. And now, okay, but that's right. So if that's correct then. What am I doing? If I put this B here and B here, oh, yeah. Let's see what's, oh, I'd like to clear this picture. How do you clear that? Yeah, I can get what I want actually so I go from B and then to get to B, I sandwich in B with B prime, and that gives me B prime here. And now I want to get back to B double prime equal to B. And I can do that by taking this expression here and multiplying both sides by B here and B here. Okay, let me see if I can get, no, this isn't right now. Okay, so, okay, let's take this, I want to get this third line. So I want to write B prime, B prime, And now I want to multiply this by B like this. Yeah, that's correct now. You see, by local duality, this is equal to B. Okay. That's what we said here. You see, B prime, B prime is equal to B. To get from this line down to here, I just multiply both sides by B prime. That's an idempotent then. Okay. But if I take it a second time, I just multiply by B instead, and then I get this third expression. So this is what I want to put here. That goes here then. Okay, and then you can see, then that just says that B double prime goes to B. And that's, of course, that's in the sense of what I call local duality. Does that make sense?
I think I see what you're getting at, but I'm not quite seeing the connection to category theory, I suppose.
Well, I'm thinking about the picture that Dr. Cruz drew on the box. He had C and B, and then he's going down the line there with that centerpiece. The picture he drew, I actually took a picture of it. I'm trying to reflect this relationship that he's trying to reflect that C and B, what he wrote down, by using this idea of local duality.
The critical part of what he was doing was to, at least at the point at which he was interrupted, was he was talking about the functor, that is this mapping that goes from one category into another category.
Can we consider this here? B goes to B prime. Is that going from one category to the second category by multiplication here? And then to get back, you just multiply by B. Well, that's the second category. If I'm in B prime, to get back to B, I have to I move back to the first category by multiplying by B.
But this functor that you've drawn between two categories is associating an object in the second category with each object in the first category. So that
and of course, I'm kind of trying to, just like in the first category, C, that's this side here, that's what he's called C here. Oops. C, and this is what he called B here.
Yes, so the objects in category C normally would be labeled something like C1, C prime.
Well, that's
like
right. I'm
C prime, C double prime.
In the category C, I'm saying in the category B, B is the same object. But now for B prime, I take, well, actually I get back to B by, that's a different element, but it's reflecting multiplication to get back to, well, then it's the same element again. And then to get B double prime, I'm replace again. Well, maybe it doesn't. Well, that's what I'm calling local duality, though. That's what but you can say that really I don't have that C is really equal to B in this case, and not really a distinct. Well, it's a different way of writing those objects. Instead of writing B prime, and B double prime, I'm writing B prime, B prime, and then B prime, B prime. That's a different object than over here, but it relates back to well, maybe I should put a dot here instead, or distinguish this equality. This equality means something than equality over here. B is equal to B double prime. Well, this is really, so maybe I should put, this is maybe a dot here or something to distinguish this equality here from over there. And then this is a double dot here or something like that. So I want to make these different categories, B and C and B are different categories by the way I've distinguished the multiplication or the equality. I don't know. Like I say, I'm just trying to copy, trying to use some of the ideas that of category theory to relate what I'm trying to describe as local duality in this way. But that's
Well,
the thing. Does that make
the
sense
type
at
of-
all?
I'm struggling to understand it. The the idea of duality in category theory that Eustace was talking about had to do with reversing the direction of the arrows, so that before we can talk about a category, we need to talk about what are the objects of the category and what are the morphisms or the arrows of the category. So then once we're given a definition of a category that includes objects and arrows, then we can talk about relating one category to another through something called a functor, which maps the objects in one category to the objects in the second, and maps the arrows in one category to the arrows in the second. And there is the constraint that the composition has to be preserved in such a
How about if we did it like this? C, then write the B category as I've written it here, but then map this with the second arrow back to D is equal to where D is equal to C then. So have a step in between maybe. Would that help anything? D is equal to C.
Yes, well, in principle, even you're talking about the application of the same of another functor which maps backwards.
So then we would be relating a category to an intermediary step to this back to the same category. That would be like going around in a circle there or something like that. So C and B would be different categories, but then we map by a categorical relationship D back equal to back to C again. So this becomes B prime and B double prime again. Okay, does that make sense? Going back, so we have two arrows and we have B going to this expression here, and then this expression going back to C again. Does that make sense?
That seems okay. I mean, the second arrow that you've drawn is the second functor that maps in the opposite direction from B back to C.
Uh-huh. Okay, well, so maybe we could.
But what you're calling arrows there are not morphisms, they're functors. So a category also has morphisms. Besides objects, you also have relationships between the objects within one category.
Well, okay. Well, like I
So
say, I'm really getting familiar with the category theory. I'm trying to.
So you have, for example, an arrow between, say, B and B prime in what you've labeled there as category C. So inside that category, there's a relationship between these objects.
Okay, so that's right. So so B is an intermediary, which I don't identify what those elements are until I map it back to the first category then. Or is that correct then? Or you call it that the mapping's a functor though, right? Between those three categories.
Well, you need to distinguish between the morphisms in the category and the functors that map from one category to another.
Okay, so maybe I would need an arrow between B and B bar. B goes to B bar, goes to with an arrow here like this, going down like this, going down with an arrow here. Does that make sense? And then the same thing here. And I don't need this here then. So we have B going to B prime, B, B prime, and then B, B prime, B, B prime, B, and then it all goes back to the same thing. Or maybe I should, maybe I should turn this thing upside down or something like that. Reverse the arrows going in this direction, or by just changing the order.
Well, that was the idea that Jesus was discussing, I think, was the situation in which the functors reverse the direction of the arrows, so that a functor can keep the direction of the arrows the same, in which case it's called covariant.
Okay, and then this would be contravariant.
But if it reverses the
last
direction
step
of the arrows, then it's contravariant.
Yeah, huh.
But there's quite a bit more to category theory than that. But it's abstract. Like, remember, category theory itself is very abstract. So when you're talking about category theory itself, you don't have any notion of operations. Like, it's not algebra. It comes before any algebraic concept. The only thing that you do have is composition, so that you can compose two arrows, provided that they share
Okay.
an object.
I think some of these issues are coming up, like I say, what I presented the last time. I think you still have a copy of that, but there's something wrong with what I did with when I tried to do this Heron's relationship, which is very interesting, using these ideas. And what was wrong is that everything was right, except I had to replace Euclidean distance with the 1/2 Euclidean distance squared. Well, so by the way, that's also what we're trying to relate it to with this Dr. Howell, is relating it to the so-called conformal model. And that's where the conformal model in Clifford algebra is where actually it's a reflection of stereographic projection. So he's able to do this Heron's formula using basically stereographic projection. But what I wrote down was not quite right, because I needed to square, instead of writing Euclidean distances between vertices, it had to be replaced by 1/2 the distance squared between vertices, which is very strange, of course. And I'm trying to understand why that is. For example, maybe, well, I don't know exactly. I'm still working on this,
well, perhaps next time you can at least elaborate on that problem, even if you don't have a solution yet. I mean, if you can describe.
Yeah, depending upon what happens in the next 3 weeks. For example, on March 24th, I guess then our next meeting will be what, 6 days plus our meeting will be on a Wednesday. So I'm giving this talk in Tallahassee on March 24th, which is a Sunday. So I guess our meeting is a couple of days, Monday, 3 days after that. So that's fine.
27.
Yeah, our meeting will be on the 27th, so that's fine. And at that time, I would like to invite Dr. Howell to join our discussion. I think it would be very interesting to get him in on it. He is interested. I've talked to him about it before. And in particular, this idea that he has of generalizing Heron's formula for a triangle to simplices, which is, well, that's very interesting what he's done actually. And he did express an interest of maybe, so I would invite him then, if that would be all right, to join us in this conversation as well, this research group.
Yes, well, especially if you could, sort of present a subject, or if you could agree together with Dr. Havel on a subject that sort of focuses on a specific issue, specific ideas, I think that would be
okay. Well, I will be discussing it more with him. We're working pretty hard actually on. We've submitted a paper to this ACOXA. It's the application of Clifford algebra to engineering and all that.
Mm-hmm.
And the next one's going to be in Amsterdam. I don't know if you've heard about it. It's being organized by Lazenby and endorsed in Amsterdam, and that'll be in August. So we put in an abstract trying to work out some ideas of Dr. Havel's using this idea. We've changed the terminology a little bit. He doesn't like the term local duality that much either, but we've introduced new terminology now. But again, this is something we can talk about in 3 weeks, and that will be after.
Some brief introduction to your abstract, and
so maybe Dr. Havel and I could present at the next session and explain some of these ideas. So he would talk for maybe half the time, and I would talk the other half, or something like that, if that would be agreeable.
Yes. Well, okay, sure. Yeah, I think that would be fine. If you just send me an email just to confirm, or just a few details.
Okay. Yeah, well, certainly. Yeah, I'm just wondering, maybe we could get back Dr. Cruz. I'll stop sharing now. Let's see.
Okay.
How do
I need to.
How do I get out of? See, I guess I can do. Let's see. How do I stop sharing? Oh, okay. I can. Let's see here.
Yeah, I see an email that says only that he lost connection. He said that the energy break. Maybe he means that he has lost power. He may. It isn't entirely clear, but it looks as if he may have lost power, so he was unable to continue.
Yeah, I don't know how to stop sharing my screen.
You should have an option near the top of the screen. It should say something like stop share or something like that.
Maybe I can just pull it down here or something like that. Okay. Okay. I can. Okay. That's it.
Yes. Yes, you've succeeded.
Okay. Well, I'm really sorry that we lost Dr. Cruz. Maybe,
Yes, he hadn't really had much of an opportunity to to complete his introduction. So, uh, depending on when I can send the email again to Dr. Cruz, I can confirm with him whether or not he might be available in 3 weeks to continue, or at the same time we could also discuss with him by email the possibility of a presentation between you, Dr. Sobchak, and Dr. Havel. Uh, that
Yeah, sure, that would be fine too.
Okay, well, we'll do one or the other. I'm not sure which. Um, at some point in the future, probably not in 3 weeks' time, but in sometime after that, I'm hoping to actually give a short presentation on something entirely different. And I don't know uh, quite how to approach it, but what I guess one thing is I would say is that I'd like to uh, see how, or to explain how one can use category theory to have a better understanding of what's being discussed as artificial intelligence these days.
Yeah, that's very interesting.
Also, I think that there's a lot of uh, a lot of problems with the way in which what has been called artificial intelligence in the popular literature. There are a lot of technical problems with the way it's presented, in that there is potentially a way to deal with the concepts in uh, what in artificial intelligence is called transformation theory. That is like uh, so one can define these transformations in a formal way in category theory, and I think that is has not doesn't have very strong connection to physics until you sort of admit that we don't have any good descriptions in physics of what we mean by intelligence. You know, like intelligence itself is something that has been treated as somehow outside of physics, uh, and so I would want to make part of the argument that that's not a natural situation, and that we should be able to deal with the notions of intelligence and language and so forth in the context of physics, especially since physics is supposed to be about nature, right? And one aspect of nature definitely is
Well, maybe
complicated
between
systems
biology
like
and physics,
intelligence.
because they're certainly making much progress on understanding all the. In fact, that's what the basic technology behind artificial intelligence is. Of course, neural networks, or mimicking neural networks, as far as training, like a child training by its parents, and so on and so on. There's many connections between biology, of course, to start how our intelligence arises. In fact, is an extremely interesting question.
But I guess I want to take a more formal definition of what it means when we talk about networks, and how networks can somehow express transformations in a way that allow us to describe what's going on when we say that some system displays intelligence. It, so it's completely abstracted from the underlying biology, but I still think it's very relevant to physics because it needs to deal with the notion of the representation of reality, in a sense that when we perform a transformation from from a statement in one language to the internal form used by some AI, we have to have a view, I think, that what the AI has internally is some kind of representation of reality, even if it's, you know, not exactly what we might think human beings mean when they say reality. Nonetheless, it has a formal relationship that so in other words, a lot of physics has to deal, at least metaphysics has to deal with the notion of what is real, and and physics is about doing calculations involving things that are real, and it gets
Well, that's
tied
interesting.
into.
I just can't resist saying that the outcome of the Super Tuesday in the United States here, that's beyond reality in itself. It's pure language, actually.
Yeah, I don't know quite how to include that in anything that's intelligent.
Yeah, well, that's
Okay.
Anyway, that's very interesting. I certainly would be interesting in such a discussion.
So I don't know if you've come across anything in Clifford algebra or geometric algebra that involves sort of the kind of networks that are discussed in artificial intelligence. That is another.
Well, Clifford algebra has been taken a lot of applications in the engineering scientific community, and in fact, in computer vision, there's all kinds of people working on that, like Lazenby's or Joan Lazenby and this Dorsk in Holland. They've been applying to vision and robotics and all kinds of things to in many different ways. And also to neural networks. I've seen several papers about neural networks utilizing Clifford algebra as well. So that's basically geometrizing AI in a certain sense, I guess you would say.
Okay, well, let's say that we'll sort of cut our meeting a bit shorter today, and we can plan to meet again in 3 weeks, but we'll leave the topic open for the time being until I get a chance to hear more from Dr. Cruz.
Well, maybe Brian has something to say.
Yeah, Brian.
I think about category theory with relation to machine learning. I think it's closer. Well, at least the research I know is have been developing. It's on the NLP part of machine learning, the natural language processing. They have like a lot of connections between category theory and that specific area of machine learning, because they use like different models to analyze the structure of a sentence or just like text in general. I think the work that I was like researching about the CX calculus, it has like a really strong relation with category theory, and it's also applied to NLP, to natural language processing. So I think from that perspective, it could be easier to see like the how they interact with each other, and how it could be beneficial to understand some properties in that sense that have an implication, and also like helping, as you said, Professor Page, to understand really what is happening. For example, in the deep learning area, most of the work that my colleagues do, it's more like a test and modify parameters kind of experiments, but they actually don't know what is happening inside of the hidden layers.
Black box.
Uh, yeah, because it's like I was like talking with a colleague the other day, and I was like proposing him like a question that is like where comes the complexity from? Do you need like a certain number of neural networks and certain number of connections to have like that magic inside the deep learning area, or is something that we don't understand that is missing on the model that is actually happening, but we are not like understanding why it's happening and how we can like take advantage of that. So I think it's
Yes,
really
I
interesting.
think,
Yeah.
yeah, yes, I think your point is very valid, is that we have this uh, phenomena that is obvious in the application of AI to language processing, and this sudden advance in almost an order of magnitude in terms of what is this type of system is capable of doing, but without an adequate theory to explain why did we suddenly see this advance? Like, was it only a matter of scale? You know, there's doing the same thing that has been done since the 1960s, but doing it at a scale of, you know, millions of well, how should I say, I mean, uh, the emphasis on large language models, where one takes language sets that are derived from the internet with many gigabytes worth of text, and then analyzing the structure of that text alone using techniques that were known already in the the second half of the last century, um, but doing it at a scale suddenly so much larger, we don't have any good theory as to why that should have resulted in such a significant advance. Yeah.
Of course, the human mind is even a much larger scale, but supposedly somewhat the same idea. So you wonder whether consciousness will arise automatically at some point.
And that's the interesting part about it. And also I have a like a similar example in the area that I research, which is optimization problems, also the SAT problems. I don't know if you are familiar with that term, which are the satisfiability problems. um, they actually uh, well, a type of those problems which are too SAT, which are limited to two variables and a certain number of clauses, can be solved in a classical computer. But when you add an extra dimension to that SAT problem and you transform it from two SAT to three SAT, it cannot be tractable on a classical computer. So everybody is like asking why that happens. It's something like intrinsic inside the problem that gets complexity just to adding one dimension, or that kind of questions. I think they are also carry on to the part of machine learning, when we are seeing that when we add more complex models and the capabilities of the model are improving, what is really behind that? How is this like simple rules that we use to model or approximate the model when we are designing the neural network, for example? How is this when we are scaling the depth of the model is increasing in complexity? How is this actually happening? So I think it could be really interesting and also really beneficial to have like a really good understanding using category theory, because it gets more flexible to generalize ideas and then have like a solid mathematical background to support it, and how we are like seeing those things. If in some years or something, someone comes with a theory on how to do it, how to translate the category theory to machine learning in general, or maybe just deep learning.
Well, that's the interesting
Yes,
about
I take
Clifford
the point
algebra.
too.
Yeah, you can expand Clifford algebra very easily by adding dimensions. In fact, that's with matrices. You can increase the size of a matrix, but it's extremely clumsy. You have to use the Kronecker product, but with Clifford algebra, you add. Well, for example, you go from a standard model to a conformal model. Then you can increase the dimensions by being able to do more and more complicated things. And maybe that's one of the reasons why it's applied to. Well, that's why I believe that category theory is related in a deeper way to Clifford algebra as well, geometric algebra. So all these ideas we're talking about, I think, are related. So it'd be very interesting exploring this dimension as you're both talking about now, I think.
Okay, well, that's good. And at least we agree in principle that it isn't going too far afield, even though it might be a stretch to still call it physics. But as Brian just pointed out, there are connections with quantum mechanics, at least at an abstract level.
Well, exactly.
And,
all kinds of things out there that are technology
okay.
is exploding.
All right. Well, let's stop for today, and hope I'll see everyone in 3 weeks. I will send an email to confirm exactly what our subject will be in 3 weeks' time.
Okay, perfect.
Okay, sounds good. See
Okay,
you.
bye for now.
See you, everyone.
Take care.